we continue with another example in which we apply Bernoulli's equation. Bernoulli's equation, as we know, is P plus half B square plus rho G H. H is the height or the distance between the 2 points where the flow field is being observed. So sometimes it is denoted by H, the height, sometimes the Y. Still, it reflects the height and it's in the vertical direction. And this has to be constant. So that is the main principle, and in which these three things are the pressure, and the pressure has the dimensions of newtons per meter square. They can also be written as newtons into m minus cube, which means we have deliberately written in this way so that we can write it as joules per meter cube. So we are trying to equate the pressure terms in terms of energy units. So this is therefore known as then the pressure energy. Then we have the other term, the middle term is half or times rho times V square. Rho is the density of the fluid under consideration. We substitute their dimensions. So half is a constant, it has no dimension. Rho has its density, has its dimensions, and the velocity is distance covered per unit square. So we make those substitutions, and that result as that simplifies in the end to joules per meter cube again. So we are trying to represent velocity units in terms of its dimensions, in terms of energy. And this is sometimes therefore known as kinematic energy. And similarly, rho GH, this force that is acting there in this equation, it is rho GH or rho GY. Both of them are equivalent and we can replace them as per our will, as we like. They have the same meaning. So as long as we know that. And therefore its dimensions, you can see, are also reduced to this. So this energy is known as potential energy because the whole contribution that is there is because of this H. The density of the fluid will not change during the movement. The gravity again remains the same, and the only thing that can change is the height. So due to that, this energy term is known as potential energy. The same thing is described here, that each term has the dimensions of energy per volume or energy density. So this is kinematic energy, and this is potential energy that is there, and P reflects the pressure energy that we have just mentioned. After describing going over the dimensions, which are trivial thing that you may already be familiar with that, we see a simple type of flow in a tube, which is of the type of Venturi tube type format. How do we measure the velocity if we want to know if the fluid is allowed to flow through the pipe from the left hand direction to the right hand direction, and in between it is connected with a Venturi type or a manometer. So therefore the terminology here, V1 is the velocity of the fluid that is denoted here. This will be H is the difference in the water levels. You can see here it is reflected from this surface to this surface. If it changes, it will change. And the other are the pressure terms. Pressure in the fluid or pressure in the manometer. We have this equation according to the Bernoulli's principle. This has to remain constant. So therefore at point 1, the same equation must equate at the point 2. Now we observe that y1 is equal to y2 and p1 minus p2 therefore will be reduced from this equation to this equation. And when we solve it further, we have P1 minus P2 is equal to density of the fluid in the manometer times GH, and by the mass is conserved, so therefore area of the cross section of the pipe into the velocity, so that the total quantity of the fluid that is there at point 1 must be equal to point 2, and from this we obtain that V2 turns out to be this equation. So therefore density in the manometer times GH, that is this term, can be written as what we see on the right hand side of the equation. And from this simple algebra, and we work out that the velocity is this term. So the question was, how do you find the velocity in the flow field in the pipe? And it's a simple application of Bernoulli's equation from which we derive this, and for a particular pipe, its area of cross section, the density of the fluid and so on, of course, will be known. And so this is what we get, and we can determine the velocity, the speed with which the fluid will flow between the pipes.